Recording right now. All right. Thank you all for joining us for our NAIRR second showcase for the NAIRR pilot project. On behalf of the User Experience Working Group, I welcome you all in our showcase. Today we have, we are thankful that we have company of five esteemed panelists who will be joining us and talking about their research projects and experiences with NAIRR, which will help the community to work on the pilot project and also on their research. So I'll start with the order of and introduce our panelists. Our first panelist is Dr. Shelley Knut. Her project is titled Access Support Project and Group. Dr. Shelley Knut is the Assistant Vice Chancellor for the Research Computing at the University of Colorado Boulder. Her team operates a supercomputer, research data storage, a secure research enclave, a conduct cluster, infrastructure support for courses, and a friction-free network for large data transfer. She's also one of the two executive directors for the Center of Research Data and Digital Scholarship, and chairs the Rocky Mountain Advanced Computing Consortium, which collaborates throughout the Rocky Mountain region on CI projects. Shelley is the lead PI for the NSF-funded Access project and serves as PI on several NSF-funded projects as well. Additionally, she leads the User Experience Working Group for the NAIRR pilot project and is a member of RMAC Women HPC chapter and holds a faculty appointment at Colorado. She earns on her PhD in Atmospheric and Oceanic Sciences in 2014. Thank you, Dr. Nut, for joining us. Our second panelist is Dr. Anju Gupta. Her project title is AI-Driven Unbiased Career Life Assessment for the Advancement Marginalized STEM Faculty. Dr. Anju Gupta is an associate professor of mechanical engineering at and the principal investigator of the Interfacial Thermal and Transport Lab at the University of Toledo. She is also principal investigator and founding director of the NSF Advance at University of Toledo, established in August 23. Dr. Gupta is also a faculty affiliate at the Center for Hypertension and Precise Medicine and serves on University of Toledo's Water Task Force for Lake Erie Research. Dr. Gupta has received funding from NSF, ONR, ACS, PRF, Ohio Space Grant Consortium, and industry sponsors. Dr. Gupta has co-authored more than 40 peer-reviewed scientific and education journals with the featured journal covers. She serves on the editorial board of Nature Scientific Reports, and among her several leadership roles, she is on the editorial board of Scientific Reports and serves as the area chair of carbon nanomaterials at AICHE. She serves as a youth chairperson and STEM mentor at the Women of Toledo, a nonprofit organization. Thank you, Dr. Gupta, for joining us. Our next panelist is Dr. Carl Boettiger. His project is titled Building AI-Enabled Data Visualization Interfaces. Dr. Carl is an associate professor in environmental science, policy, and management at UC Berkeley, a theoretical ecologist and data scientist. He works on ecological forecasting and decision-making under uncertainty. He has degrees in physics and population biology from Princeton and UC Davis. He's a co-founder of Schmidt Center for Data Science and Environment at UC Berkeley and of open source community projects like rOpenSci and Rocker. Thank you, Dr. Boettiger, for joining us. Our next panelist is Dr. Pradeep Dasigi. His project title is Enabling Advanced Reasoning and Scientific Text Understanding in Language Models. Dr. Dasigi is a senior research scientist at the Allen Institute for AI, where he focuses on building usable language technologies. He is involved actively in the development of AI Square open languages model and is passionate about adapting language models for broad and general purpose use with minimal human intervention. His research interests span across parts of post-training pipeline, including efficient data curation, robust learning algorithms, and fair evaluation. Thank you, Dr. Dasigi, for joining us. Our last panelist is Dr. Chandi Witharana. His project is titled Use of AI and Sub-meter Resolution Satellite Imagery to map permafrost thaw disturbances and human-built infrastructure at pan-Arctic scale. Dr. Witharana is an associate professor of remote sensing at the Department of Natural Resources and Environment at the University of Connecticut. His research efforts broadly captured the methodological development and adaptation to unseal faster, deeper, and more accurate analysis of large volumes of multimodal, high-resolution remote sensing data captured from mobile, drone, and satellite sensors. He conducts interdisciplinary remote sensing research and with the environment in industrial and in agricultural application. Thank you, Dr. Witharana, for joining us. With that, I will say that thank you all for joining us again. And Shelley, it will be our first panelist. Shelley, it's all yours now. You can share your screen.
You see my screen? Perfect. Thank you, and welcome to our AI showcase. We are glad to have you here. Before the panelists get started with their research, I wanted to share a bit about the National Artificial Intelligence Research Resource Pilot and make sure that everyone knows what this is. And it's a pilot that is connecting U.S. researchers and educators to computational data and training resources needed to advance AI research and research that employs AI. It's a high-profile project. It's come from an executive order from President Biden, and it combines several federal agencies who are collaborating with government-supported and non-government partners to implement the pilot as a preparatory step toward an eventual full NAIRR implementation. The pilot helps bridge the gap for researchers who lack access to AI resources needed to conduct research, and we aim to ensure that AI resources and tools are equitably accessible. So what's available as part of the NAIRR project? Well, if you applied to be a part of NAIRR, or I should say the NAIRR pilot, if you apply to be part of NAIRR, you get access to some of the premier AI resources in the country, which includes computational infrastructure, tools, models, and software, data sets, and training and educational resources. You might be asking, well, who's it for? Is it for me? It is. It's for everybody. It's right now we have some calls for researchers and educators. Maybe you're already using AI in your research or in the classroom. Maybe you're not yet doing so, but you want to get involved in some way. All skill levels are welcome. All of you are invited to participate. How do you get involved? Well, if you have a project in mind, you can apply for one of the open NAIRR pilot calls, the NAIRR pilot resource request to advance AI research, classroom educator resources call, open data, models, and more. There's also an opportunity through a Dear Colleague letter put out by NSF where you can apply for either supplemental funding or an eager grant if you have an idea of another opportunity for NAIRR. If you're not sure about a project, we invite you to contact us and we can help get you started and get you going on the pilot as well. I wanted to point out, the intimidation factor. Sometimes people think, AI, I don't know enough to be a part of this high-profile project. I mean, it came from the president, right? How could I possibly be involved? And, it's for you. It is intimidating, but it's for you. And you should work with us and we will work with you to get you as part of the NAIRR pilot. So if you don't know how to start submitting a proposal or it looks too intimidating, it's really, no problem. We'll help you. You can submit a ticket and you can meet with someone from our team who will guide you. And the nairrpilot.org is the place to go. And I think I had that on the previous slide. You can connect with us on that. If you're worried that you don't fit in here, you do. And we have a team of people to help you. We are poised to be able to get you as part of this pilot project. And we want to make sure that you understand that you're not behind. We're all starting this together. AI is AI, and we're all in this together. We really want to hear more from you. So within this AI showcase, we're going to do some surveys because we're planning on doing a workshop coming up here in the spring. We're looking at being able to provide travel support for participants. And this workshop is really for you all to help get you centered around AI. It's on our events page, and there's also future events will be on the events page. But you can learn about other future events as well. And then finally, I wanted to make sure to introduce the NAIRR pilot user experience working group. Our members are myself, Nitin, Alana Romanella, and Marisa Brazil. And we're really the ones here that are putting this on. And our goal with NAIRR is to help guide the user experience. We want to make sure that we understand what that user experience is like and then make recommendations so we can best meet the needs of users. Right now, we're offering office hours, consultation, we're answering tickets, we're doing everything that we can to guide you through this process. And we're also providing trainings and webinars like this one. So again, we're here to help and we're here to guide you. The user experience working group works with resource providers, other NAIRR pilot working groups, and other teams that are working as part of this project. And I think I saw somebody's hand go up. Nitin, do you want to take questions now, or how do you want
I think we should wait. We already have the Q&A session running in the
to? Okay,
Q&A. Please do that. I think we can move to the panelists, right?
perfect. Well, let me offer up our first poll while the next panelist is getting her slides ready. But yes, please answer your or ask your question in the Q&A, and thank you.
I think Gupta, you can start sharing your screen, please. In the meanwhile, we answer the poll.
So our first poll is, why are you here? Getting close. A couple more, you want to chime in? Awesome. All right, going once, going twice. Okay. Here's the results. Quite a number of you are interested in learning about the NAIRR pilot, which is awesome. But yeah, we have folks who want to just learn more about AI and what's possible in research and classroom and everything surrounded with AI. So thank you. We'll have a couple more polls throughout. And feel free to put your questions again in the Q&A.
Dr. Gupta and Payal, you are good to go. Thank you.
Thank you, Nathan, for the invitation to talk. Good morning, good afternoon, good evening, everyone. It is my pleasure to share our AI-driven project with you all. With me is Payal Bhattit. She is the graduate research assistant on my NSF-funded Advanced Catalyst project. In first few slides, I'm going to describe the Catalyst project that led to data and that led to the computing hours for NAIRR project. And Shelley, thank you for bringing up the intimidation factor because I was one of those faculty. I recognized my project was more social science based. And when we look at AI, we think it's all technology based. We still took our chance. I collaborated with Dr. Dinakar Rao from George Mason University and Dr. Amlan Ganguly from Computer Science Department at Rochester Institute of Technology. Together, we submitted this proposal, and I'm so glad it got funded. So next few slides, I'll briefly go over the project. Sorry. So the motivation behind our project was to have an AI-driven inclusive lytics. We wanted to develop an AI model which is bias-free and that can detect the belonging and accessibility among faculty for the long-term goal of promoting gender equity among STEM academic professions, which is also one of the goals of NSF Advance. We requested for a couple of cores GPUs for our computing models, and we were trying to create a faculty career life survey that would get us data in terms of qualitative and open-ended responses. And we focused on large language models to understand the open-ended responses and then create our codes to detect any biases or no biases. And I'm here to discuss this project because I'm looking for partnerships, training opportunities to improve my AI skills, looking for additional resources and networking opportunities. So in next two slides, I'll briefly talk about the advance at UToledo and the vast amount of data that was produced through this project. So we were established in August 2023 through NSF-funded Catalyst project. Again, our mission is to promote organizational change, and that was through collection of data, self-assessment of faculty, administrators, staff. And this was done by an extensive survey that had 6 different categories of questions, starting from salary, startup funding, courses that they are teaching, other teaching and advising responsibility, research, resources, scholarly work, and so on. So this was our survey, and our goal was develop the survey, go through the IRB approval, administer the survey, collect the data, and then perform AI analysis. So our data was collected through 288 questions that entailed both quantitative and qualitative. We had a total of 290 faculty that took our survey, and the questions were divided into 11 categories. I'm going to pass the stage to Payal, who's the computer science expert on this project, and she'll briefly talk about how we are implementing AI and machine learning on this project.
Thank you, Dr. Gupta. Hello all, and from this slide, I'll be going to discuss the artificial intelligence aspect of this project. As Dr. Gupta mentioned, we had both quantitative and qualitative data. So for quantitative analysis, we utilize tools like SPSS, Pandas, NumPy, which is to handle statistical processing and exploratory data analysis efficiently. So given our data size, processing on standard CPU was manageable. However, scaling to millions or billions of responses would impose a heavy computational burden on a CPU, making it challenging to execute real-time processing and advanced analytics at scale. In such cases, leveraging distributed computing or GPU clusters would be essential to handle the increased data volume, computational load, particularly for training more complex machine learning model. On the other hand, we have qualitative data, which is often underutilized in analysis. It is frequently summarized by human reviewers, a process prone to subjective biases and inconsistencies. Unlike quantitative data, qualitative analysis possesses unique computational challenges, particularly given its unstructured nature and the complexity required to extract meaningful insight from these texts. So to address this, we opted for state-of-the-art transformer models and advanced language models, specifically designed to handle natural language processing tasks at scale. These models, due to their high dimensional architecture and reliance on attention mechanism, demand substantial computational power that far exceeds the capabilities of standard CPUs. And running such model on a CPU, regardless of the data size, is highly inefficient and often infeasible due to prohibitive processing time. So to overcome this, we use GPUs and TPUs, whose parallel processing capabilities allow us to execute deep learning tasks effectively and handle such unstructured data set, resulting in accurate and unbiased analysis. So yeah, next slide, please. Yes. Thank you. So here in this slide, we present the output of a sample predictive model developed to analyze factors influencing faculty satisfaction across 2 primary groups, Group A and Group B. Using Python libraries like scikit-learn and Pandas, we built a machine learning pipeline focused on data from one category. So this approach allowed us to identify key drivers of satisfaction, showcasing how machine learning can effectively reveal factors specific to each group. So as you can see on the left, we see the features with the highest impact on satisfaction for each group. For Group A, scholarship emerged as the strongest predictor, while professional services was most influential for Group B. These variations highlight the need to customize approach based on group-specific insights. And on the right, there is a classification report detailed the model performance, showing a robust accuracy of 86% for Group A and 92% for Group B. These metrics emphasizes the model's efficacy in distinguishing satisfaction factors, effectively leveraging supervised learning technique to identify patterns within our data. Next slide, please. So, coming back to qualitative analysis, we'll be diving into advanced AI techniques, specifically sentiment analysis and topic modeling using transformer-based language models. These are kind of tools that big tech companies like Google, Microsoft, Amazon use to make sense of unstructured data at scale. Now, let's look at this example on the left. This sample faculty response contained both sentiment and topic, like faculty recognition and merit raises. To analyze feedback like this, we need some serious NLP technique. So the process starts by tokenizing the text with the BERT-based tokenizer. Essentially, it breaks the text into smaller units called tokens while keeping the context intact. This is the key for capturing the nuances in feedback like this. After tokenization, we can either use pre-trained model to classify the sentiment, or if we want even more accuracy, we could fine-tune the model on our specific data, though that's going to require even more computing power. Now here, because of the phrases like not good at recognition, would likely push the model to tag this as a negative sentiment. Now coming to topic modeling side, the language model picks out key themes like merit raises, recognition. This helps us spot pattern across the data, giving us a clearer picture of common concerns in faculty feedback. Now, one of the biggest challenge with this transformer model is their demand for computational power. These models have billion of parameters, and if we were to run them on a regular CPU, it would be painfully slow. This is where GPUs and TPUs come in, especially GPUs like NVIDIA's A100, which is built to handle this kind of workload. There's high memory and processing power make a huge difference, letting us process large amount of data quickly and accurately. Now, if we are working with limited data set for training, we can turn to synthetic data generation. This approach is gaining traction as NVIDIA even calls synthetic data the future of AI. It lets us expand the data set without needing additional real-world data and helps reduce biases and boost the model's performance. So in short, by using sentiment analysis, topic modeling, and some serious computing power, we were able to break down qualitative data into actionable insights. And this kind of approach gives us a scalable way to understand faculty feedback in depth. Next slide, please. All right, then to wrap things up, let's go over the big takeaways from our analysis. First off, high performance computation. When you are dealing with large unstructured data set, you need serious computational power. This lets us process data efficiently, getting real-time analysis and quick insights. Next, we have scalable NLP model. Transformer-based model are a game changer here. They allow us to find pattern in extensive data, patterns that are usually tough to quantify. This scalability is key for digging deep into qualitative feedback. Then there is minimizing biases. By automating the analysis, we reduce the human subjectivity that can sneak in. This makes our findings more objective, reliable, and scientifically sound. And finally, resource-intensive processing. Training and deploying this NLP model isn't light work. It requires a lot of computational power or GPU or TPU power to handle the complexity and scale. Without these resources, this kind of analysis just wouldn't be feasible. So these insights really highlight the importance of solid computational infrastructure. With the right tool and advanced model, we are able to drive analysis that's unbiased, scalable, and accurate. Now, with the support of NAIRR, we were able to process our data efficiently and at scale. NAIRR's resources not only help streamline our current analysis, but also hold the potential for expanding our work. Let's suppose if we were to work with unstructured data formats like audios or videos, potentially in gigabytes, NAIRR would enable us to handle these data types seamlessly, further enriching our analysis. So NAIRR provides a valuable framework for leveraging AI resources in various ways, making it an invaluable asset for large-scale data projects. The computational support and resources from NAIRR empower us to push boundaries in data analysis and handle increasingly complex unstructured data with ease. With that, I would like to thank you all for your attention. And yeah.
Thank you, Dr. Danpal. Shelly, it's time for the next poll. We'll take questions in the Q&A, and Dr. Boettiger, you can start sharing your screen, please.
Okay, here's our next question. What is your experience with artificial intelligence? Okay, going once, going twice. All right. Most of you said that you know what AI is and what tools are available, but there's quite a number of you that have heard about AI but don't necessarily know how to apply it to your work. That's fantastic. Thank you.
All right, Dr. Boettiger, you can start. Thank you.
Hello, so I'm Boettiger from UC Berkeley. I'll be talking about using AI in the classroom. So I'm an ecologist. This is my classroom. I teach SPM 157, Data Science for Global Change Ecology. This is a large class of 122 students. You can see some of them in the photos here. And about 2/3 come from a biosciences background or conservation resources background, for whom this is probably their first course in computing. About 1/3 come from a data science background, for whom have maybe one semester of prior exposure to programming in R or Python. And in this course, I try to wrestle with the questions of teaching them kind of basic computing skills that we need for modern day global change ecology, looking at big scale data and understanding the patterns we see. So motivations for applying for this. I saw the call for the NAIRR pilot, and of course, we all know that these large language models are here. They're being used by our students, whether we tell them they can do that or not. And I had to ask, as I looked at syllabus after syllabus that just said, use of generative AI is banned in my classroom, am I preparing my students for a future where they're moving into a world of language models? The questions that I had in doing this were, would it actually help them code faster or better, help me get into more complex topics if they had the assistance of an LLM? Being an environmental science class, of course, we had to also ask, though, what are the environmental implications of doing so? We know that these things, for instance, have been at least reported for very large energy footprints. And beyond the environmental implications, there are many other ethical implications in bringing these tools into the classroom that we would have to wrestle with. And lastly, as we use these, can we make the tools both more reliable and safer for their use in the class? So, computing resources that we requested. So I applied more or less on a whim to the NAIRR program and received this email saying you have been awarded a allocation on the National Research Platform, which I had never heard of. And I think I actually filed a ticket saying, after looking briefly at this, being like, oh no, I can't do this. This is going to be much too hard. And can I please move my allocation to something else? But luckily, I couldn't actually figure out how to file the ticket correctly, I think. So I didn't get a reply, and I figured I better look at the documentation and just give it a go. And I did. And I was very quickly astonished at just how far I was able to get. So I would need a GPU for each student for them to be able to play with their own language models. Well, I could just request each student gets a GPU. I have 122 students. That's a lot of resources. They gave me this little template in which I could say this is what a compute resource for each student needs to look like: memory, CPU, GPU. And by not indicating the architecture, I just get one NVIDIA GPU. If it's a high-end one, they slice it into somewhat smaller slices. I can then specify using Docker my Jupyter environment, all of the software we were going to need for environmental science, a lot of satellite imagery processing, a lot of basic data science processing with SQL, FTP kind of stuff. And boom, my students could simply go to a URL on the National Research Platform specific to my course's namespace. They could select any server options I pre-configured. I just gave them one option, use our pre-built image, or just for fun, we can bring your own image, and bang, they're in Jupyter, ready to go, except now with a GPU under the hood. You can see that we have enabled one of the new features in Jupyter, Jupyter AI. I've got the Jupyter AI tab open here, where within their own Jupyter environment, they can all of a sudden start talking to a language model and ask it to make a notebook, ask it for particular coding help right alongside as they're programming. So the challenges, I mentioned the ethical challenges. We're worried about student data privacy. We're worried about our energy footprint and various other concerns, from what the resources or labor practices involved in training the data, to possible biases in the data, and so forth. To investigate these things, I want my students to kind of take a step back from the sort of hype around sort of AI as just a thing and be able to see it as many things, and in particular, many models. Drawing from previous Berkeley faculty, Lang Winner, has pointed out that in 1980, no less, those that describe sort of the computer and its social impacts that these new technologies kind of happen, and then society has to respond, kind of miss the big picture. The big picture being that those models themselves are built in a social context for particular use, and we need to understand the context in which they're built, not just the context in which they react. So being able to explore different language models, I think, opens the door for that for my students, and in particular, to be able to look at open models that they can then run on their own machines, see things like how the models work, see things like how much energy they're using, and so forth. So in Jupyter, they have a Llama enabled. They can start grabbing a variety of different open models and start running those models directly in the Jupyter AI assistant. You can see here choice of different embedding models, as well as choice of different instructor language models that they can speak to. And in the background, we also run the Code Carbon project on the image, and they can look at the actual energy use of those models. For models that are local, that are maybe 7 billion parameters, maybe 1 billion parameters, the energy use is often way, way less than the energy use is reported for the large commercial models. And so I think this was both kind of bringing more nuance into some of these concerns, and also understanding that many of these models are trained on open data. We've just added the Allen Institute's Olmo model, for instance, where the model's trained top to bottom on open data with open code. We've also added Berkeley's Gorilla model, which is also an Apache licensed open source model, so that they can see kind of the space of options there. To make those models available, including these researcher-developed models, including ones being built right here at Berkeley, we can serve those models themselves much more efficiently by leveraging the National Research Platform, NRP, in a slightly different way. Rather than having each student run a copy of that same model locally, I learned through the instruction of some of the folks in the on the NRP platform that we can just host those models through VLM and have all the students access that directly over the API. So they speak directly to, I'm showing the light LLM interface that I get. We have a different set of model hubs. I or other researchers can add models. I just put this Gorilla model up from the UC Berkeley team, particularly because it supports function calling, another tool we're going to investigate in the last couple of weeks of our course, having the model not just give back language answers, but be able to be provided with different tools, like a Python set of Python functions, and choosing which function to call and how to call it. Now, it's relatively straightforward for the students to then be able to directly interact with these models, even from their local laptops, while the computation is able to run on the NRP platform. So there are other challenges we have run into in the classroom in using these things. One of the most common and frustrating ones is that the LLMs simply don't know the most modern methods. For instance, I give an example here where I ask it for Python code to plot all the buildings in New York City, and it says, "What a fascinating task. Unfortunately, it's not possible, blah, blah, blah." It is possible, it doesn't know the right tools. So we get a copy of the leaf map package, and I point the leaf map package, the LLM, at the documentation for just that package in leaf map using these retrieval augmented generation. I just tell Jupyter AI, learn those documentation. Now, instead of getting this kind of the mismatch of different methods that are available on the internet, often older methods, It can only give me an answer based on the documentation of that particular package, which is the one I'm teaching the course, and I know has the ability to do this. And of course, it generates code that works for this task. It says, here, you can do this using PM tiles, a tiled, cached, cloud-native format that allows us to do really large-scale data analysis like this and visualization. And so here you see several terabyte data set being accessed remotely and being run in this Python code, copy and pasted out of a notebook, and bang, I have all of the buildings in New York rendered in an interactive 3D environment. So to zoom out, in conclusion, I think one of the things that we've seen in this class is that rather than say we can't use AI, we can teach safe ways to use the language models, whether that's choosing the model that we use, teaching the model to use, and the students to use approaches like RAG, like using an embedding model to talk to the documentation and not just get whatever back. Understanding the energy use, being able to control things like privacy by having everything local to the students, and then being able to improve our innovation rates by having this sort of ecosystem where we can share hardware, software, and models, bringing in models from the front ends of research and putting them at the fingertips of the students. Thank you.
Thank you, Dr. Boettiger. I think we take a quick Q&A in the chat or the Q&A section, please. I think, Shelly, it's time for next poll.
Yep.
And then meanwhile, I think we can have next panelist who can start sharing a screen, please.
So this is specific to our in-person workshop that I mentioned earlier. Again, we might be able to have travel support. We're trying to figure out what topics we want to have and are looking for input from all of you. This is the most important question that we're asking, so make sure you fill it out. Sorry, I'm still rolling in. So
Dr. Dasigi, you can start sharing your screen now. I think the meanwhile, we just close the poll.
yep. All right, going once, going twice. Yeah, so a lot of you are looking for examples of how AI is used in research and deep dives into AI tools and all kinds of stuff. So thank you.
All right, next panelist, we have Dr. Pradeep Dasigi. You can share your screen if you can. Okay, thank you. You're muted right now.
Can you hear me?
Very good, thank you.
Oh, thanks. Yeah, all right. Hello everyone. My name is Pradeep Dasigi. I'm a research scientist at the Allen Institute for AI, where I've been co-leading the post-training of language models team. And one of the focus areas of this talk would be post-training, and particularly I wanted to talk about how we've been working on building open language models with optimal human AI collaborative supervision. Um, so, right. Before I talk about the core work, I'd like to set the context of open language models, our research focus on building open language models. It's important to note that open research in any field generally requires accessible and reproducible artifacts. And particularly in the context of language modeling research, what open research here means is releasing trained models, intermediate checkpoints of the training process, most importantly, the training data, and also the data curation recipes, and importantly, the framework for reproducible evaluation. This has been an important priority for the Open Language Modeling Project, also known as OLMO project at AI2. And the work that I'm going to talk about now is in the context of the OLMO project. Particularly, the part of language modeling research that I'm focusing on is post-training of language models, often also called adaptation of language models. Some of you may already know that the training procedure for language models typically involves two stages at a high level, pre-training and adaptation. And it's important to note that right after pre-training, a language model is not directly usable because it's not safe or robust for public use. And these language models typically require an additional adaptation or an alignment step so that language models are more aligned with human preferences. And in this process, the adaptation process, or the also known as fine-tuning process, language models are trained to follow natural language instructions, be aware of harmful behaviors, generally respond to human preference, and most importantly, improve their core skills. And it is this part of improving core skills that I wanted to talk about. The focus of our NAIRR proposal was particularly improving the reasoning and scientific text understanding of language models. Our high-level plan for doing this was to focus both on the training and the evaluation of post-trained language models. So in the context of training, we have been working on building optimal human AI collaborative supervised models and decomposing complex tasks for getting more efficient supervision from humans. And in the context of evaluation, we're building evaluation procedures where we can automatically evaluate trained language models, but in a more reliable way, so that even though they're automatic and fast, we want them to agree well with humans. So that's the high-level plan. And we, as I had mentioned earlier, our focus here is on supporting open research. So we plan to release all the artifacts that we developed during this process. The focus of this talk is the optimal human AI collaborative supervision part. Because we're short on time, I won't focus on the remaining parts. The resources we requested are OpenAI credits from Azure. From there, and we have been pretty happy with the resource that's been provided, and I'll highlight the parts of the project where we're actually using these OpenAI credits. Right. So as I had mentioned earlier, one core component of adapting language models to make them usable by the general public is aligning language models with human preferences. One important part of aligning language models is this step called preference tuning. And what that means is, and the way it works at a very high level is that given an example user input, like as I'm showing here in this case, explain how entropy can cause the heat death of the universe. That's one potential user query that a language model might see. We show the language model that's being trained two potential model responses, two potential responses that it could give. along with a label that, along with explicit supervision saying which of the two responses is better. That's the way preference tuning works. I won't get into the training details because that's not the focus of this talk, but particularly from the data perspective, that is how the supervision works. So we have these queries and candidate model responses and a judgment showing which of the responses is better. Now, an important question here is, where do these judgments come from? Traditionally, we've obtained these judgments from humans because we want to align language models to human preferences. But more recently, we have also been using judgments that come from already trained large language models. Now, there are pros and cons on both sides of obtaining these judgments from humans or large language models. Humans are generally better at certain expert domains. And as you might imagine, getting human responses or human judgments is typically expensive because we need to hire experts to do this. And there also, the judgments that we get from humans is also high variance because also has high variance because humans, can get bored or of providing us lots of judgments, or there could be some subjectivity involved in making certain decisions. Given all of this, their judgments are generally prone to being high variance. On the other hand, getting these judgments from language models can be cheaper and reproducible, but often language models can make mistakes, as one might imagine. So the core research question we had for this project was whether we can ask human experts to judge responses selectively. That is, can we choose a subset of these preference instances that we show to the humans and essentially develop an algorithm for routing only the relevant judgments to humans. The way we did that is by modeling the utility of human annotations. So that is, given a data set of these example user prompts and the candidate responses, can we look at different subsets of this data set and identify and essentially model whether getting human labels for the specific subset would be helpful or not. And the way we did this is by running lots of simulations. So given a data set which needs to be labeled, we identify multiple subsets of the data set. And for each subset, we try to obtain features of that subset and simulate a condition where that subset is being labeled by humans and actually train a model on that hybrid data set. Look at the performance of the trained model. Do this multiple times and essentially get a mapping from our feature space to the performance of the trained model. So intuitively speaking, what this is telling us is for an arbitrary combination of features, if humans provide annotations for the instances with those features, how much would the performance of the trained model improve? Or to put it differently, how useful are human annotations for a specific feature combination? Now, once we model this mapping from feature combinations to the performance of the model, routing the annotations to optimize for model performance is pretty straightforward. So given a data set, we look at which subset would maximize the performance and labeling which subset by humans would maximize the performance and show them that subset. So that's essentially the general idea. Right. To operationalize all this, we collected a large data set with preferences with both human and large language model, more concretely GPT-4 preferences, and ran simulations on this data set and trained a model to route to do this optimal routing to humans. And the GPT-4 preferences that we got are by running OpenAI models using the Azure credits we got from there. So This actually proved to be pretty successful because firstly we see that the routing model that we trained was able to identify optimal routing strategies, which means that for any given budget, so let's say you have a data set and you're willing to get only 25% of the data set labeled by humans, instead of randomly choosing 25% of the instances in the data set to show to humans, using our routing method often yielded better models, better trained models, as you can see in the plots here. And what's remarkable is that not only on the data set that we trained the routing model, even on a bunch of other data sets, we saw that these results generalized. So which basically means that the routing model we built is learning something more fundamental about what kind of judgments humans are better at making, or what kinds of judgments it's more useful to ask humans. And also, we see that across a range of budgets, we just getting preferences only from humans exclusively or only from language models exclusively is not the most optimal choice, which supports our initial hypothesis that there is this trade-off, and the most optimal method is to have only a portion of our instances annotated by humans. We published our findings in this paper.
Dr. Dasigi, we have to move on to the next presentation because I think we have only 6 minutes left. So,
cool.
Yeah.
Okay, yeah, that sounds fine. Yeah, I can conclude by saying that this is all part of this large work where we intend to continue releasing open models. So check out our upcoming releases.
Thank you. Sorry about that. Dr. Witharana, I think we are very short. I think with respect to time now, I think you can quickly, show us your slides, and then we can move on from there. Thank you, Dr. Dasigi.
And I'm going to launch the last poll
Yeah.
while you all are talking.
All right, Nitin, do you see the screen?
Yes, we see it. You're good. You can just slideshow, please. Thank you.
Make it bigger. How about now? It's good?
Yeah. Yes, good.
All right.
Thank you.
So thank you, Nitin. So I'll go quickly, right? So
thank you. Sorry about that. It's just like I think.
No worries. Yeah. He'll come back later. So yes, I'll directly jump into the topics. That's how we use large volume of satellite images to monitor the features in the Arctic and how they respond to the climate change. So this is part of a very large project currently I'm involved in. It's called Permafrost Discovery Gateway, that we try to bring in algorithms, pipelines, and visualization to uncover very intricate patterns in climate change and how Arctic is responding, funded by multiple NSF and Google Foundation awards. So this is a multinational, multi-institutional effort, Woodwell, Alfred Wegener, and NCSA, and many collaborators. So I am doing the feature detection part of this project using satellite images. So the big question is how Arctic is responding to climate change and how we can monitor what is the carbon, hydrology, vegetation impacts, and also what is the impact on communities, infrastructure, and economy in the Arctic. So now very quickly, due to permafrost thaw, and changing Arctic could impact the communities, coastal erosion, and interior Alaska. Wherever we experience these permanently frozen ground are prone to thawing, and eventually vertical settlement of the ground can impact critical infrastructure as well as communities and change the overall earth and environmental dynamics in the system. Right, so if I put a dollar value, just the permafrost thaw impact in Alaska alone, it's around $2 billion. That's the projection if we do nothing. So the big question is, we have a huge amount of Earth observation data, right? Petabytes of data. Now we need to bring algorithms, compute, and create science-ready products so that we can share the data with the Arctic research communities and the policymakers. Right, what is permafrost are very quickly, it's the permanently frozen ground. Anything below 0, that's permafrost. So what you see on your left, that's the permafrost domain, right? So the continuous, discontinuous, and sporadic. So the ground is pretty much frozen in dark or the deep blue areas, which is known as the continuous zone. So the Tundra domain itself, it's 5 million square kilometers. Permafrost domain alone is 20 million square kilometers, just to give you some kind of understanding of how large the domain is. So if I way zoom in satellite images, we see these kind of landforms scattered in the permafrost landscapes. Right, so how do we observe this hostile terrain, very remote, huge? Fieldwork is not logistically viable. So we can bring in satellite images to look through the landscape from watersheds to individual feature types. It could be human infrastructure or natural features at sub-meter scale. That's a place where we can bring in commercial satellite images. The nominal resolution is 30 centimeters, so you can easily see these features. Right, so since 2000, we have been imaging this region, and millions of satellite images acquired at 0.5 meter resolution. Close to 5 petabytes of data. What do you do with this data? That's the place where we need to bring in these kind of pipelines. So this is some kind of a matured project, right? So we are building and we are using existing computation resources from NSF like Frontera, Lone Star, Bridges, and Delta. And so we are ingesting large volumes of images into our pipeline and then do AI run algorithms and then produce a lot of geospatial data that could feed downstream tasks. And we are working with Vision Transformer architecture. That's the whole point of this request, to create a new architecture based on some of the existing architectures and to embed spatial heterogeneity in the system to this transformer. I don't have time to get into details, but I will quickly show you one product we created as a highlight using huge volume of satellite images over the Arctic, and we mapped a landform called ice edge polygons across the Arctic domain, and we identified whatever the object you see on the screen, 1.5 billion individual objects, thanks to NSF resources. And these AI models, and it's published in Nature, so you can see it, and across the domain. And so we burn a lot of service units and a lot of resources. And so these are the challenges we come across. So Nitin asked to list, and I don't have time to go over, but I'm happy to share these are the challenges we usually come across with this shared system. From there, I'll stop. Sorry, I had to be very quick, but I'm happy to answer, and you can email me. And yeah.
Thank you for that. Witharana, this helps a lot because it's right at time. It's a seminar kind of a format webinar, so we have to kill it. But thank you all for joining. Thank you, the panelists, for your help. And if you have any questions, feel free to reach Dr. Witharana, and or us. We can forward the slides, and then we will keep everybody in loop. With that, we should see you all, some of you, in spring next year, and then with our workshop. Thank you all for joining. Thanks, Shelley. Thanks all panelists.